Hello, my name is Patrick Gavigan. On behalf of myself and my PhD supervisor, Babak Esfandiari, I'm presenting our Engineering Multi-Agent Systems paper, Quantifying the Relationship Between Software Design Principles and Performance in JSON, a case study with simulated mobile robots. As many in the EMAS community are no doubt aware, belief, desires, intentions, or BDI agents, and of course implemented in JSON, provide a rationality model for agents, where these agents choose plans to achieve goals that they believe are motivated and possible. It also uses the AgentSpeak language, which provides us a declarative style of programming. Now, we wanted to look at these agents from the perspective of software maintainability and complexity, and compare how different types of design approaches that we could take with these agents what kind of effect that has on the performance of those agents, and try to quantify this relationship. I mean, looking at performance, we looked at this in a simulated collision avoidance scenario using a car in AirSim. So for the methodology, there's sort of three main components here. First is looking at different alternative implementations, and we'll talk about the details of those implementations in a couple of slides. We've got the stop trials, which are these collision avoidance scenario tests using AirSim. And we've got the results, which are going to involve the software properties, which we'll talk about shortly, but those will include coupling, cohesion, and cyclomatic complexity, as well as looking at performance, looking at the reasoning time and the response time in the collision avoidance scenario. So first, let's look at this idiomatic agent, the first of our design alternatives. Now, there's a couple of features to this. One is we have a customized event and option selection function. The event selection function prioritizes safety-related triggering events over movement triggering events, and the option selection function prioritizes non-default plans over default plans. Now, what this does is allow us to put our plans in the plan base in pretty much any order we want without concern for how they're going to be selected. So default plans can be listed anywhere in the plan base, and we don't have to worry about having mutual exclusion between our plans to make sure that only the most appropriate plan is selected. Now, it makes those decisions by having prioritization beliefs associated with the behavior. So if we look at box 1 at the very top, we have movement for waypoint, identifying that the waypoint achievement goal, or the waypoint trigger, which happens to be an achievement goal, is associated with moving the agent. And if we look at the top of box 2, we have the obstacle trigger is associated with safety. So that will be prioritized over movement-related plans. Now, there's also a separation of concerns here between collision avoidance and maneuvering the car. So maneuvering the car is handled completely without concern for the collision avoidance scenario. So those concerns are very nicely separated. And we found this, we think that this is a nice idiomatic way to design AgentSpeak code. Now, going to a design extreme, we have the goal-directed agent. Now, not necessarily how we would design an agent or would recommend designing an agent. What we've done here is used exclusively achievement goals. In this case, the waypoint achievement goal is shown on box 3, where the collision avoidance and control of the vehicle driving down the road have been combined into a single set of plans following from this waypoint goal. You're looking at another extreme is this reactive agent, which goes extreme in the other direction. So instead of achievement goals, we're using exclusively belief-triggered plans. Again, not how you would want to design an agent, or even we would recommend designing an agent. But these choices have made for two reasons. One, we've actually seen, anecdotally at least, when people are learning to program in AgentSpeak, possibly a tendency to gravitate towards using either one type or the other type of plan, but also to try to expose differences in how JSON deliberates on the types of plans or the types of designs that may come from the consequences of using exclusively belief-triggered and goal-triggered plans. And lastly, stepping out of AgentSpeak, we've got what we call the imperative controller, which is just a Python if-then-else block. Now, this obviously works without the benefit of the reasoning system, but is meant to implement a sort of complementary behavior of driving down the car down the street, which is very similar to the way the other agents were driving, of course, without the benefits that the reasoning cycle affords us. So first, we've looked at the software properties from the perspective of maintainability, and this was inspired by the object-oriented community, looking specifically at coupling and cohesion, where those metrics have been found to be tied to software maintainability. This idea that of looser coupling means that we have when you have changes to your software, those changes ideally shouldn't be breaking your code elsewhere, and then in turn requiring changes to other parts of your code. And if you have higher cohesion, that means that your classes or methods, at least in object-oriented software, should be responsible for only a single concern, which in turn makes them more reusable. So we took these concepts from object-oriented software, and we were trying to figure out how to apply these concepts to AgentSpeak software. Now, we've seen example lists in multi-agent systems, and I discussed that in the paper, but a limitation we had was we don't have a formal definition in terms of how this is used, and certainly there's a very limited practice of doing this out in the multi-agent systems or even an individual agent perspective. And of course, there are perhaps other useful metrics, but it's better than lines of code, at least we think so. And so to do this, sort of accounting for these limitations, we came up with sort of three key metrics to use to try to assess the interconnectedness of the plans within the individual agent. And so one was to look at the number of plans triggered by each event. Another was to look at the number of logic expressions in the context. The idea being if you had more plans per event and more logic expressions in each context, you're more likely to have interconnections from those different terms or expressions. And lastly is the number of concerns that are addressed by each triggering event. Now, the idiomatic agent was found, at least using these metrics, to have the loosest coupling and the highest cohesion. We also looked at this from a complexity perspective using McCabe's cyclomatic complexity. Now, this was a little bit easier to work with because we have a nice little equation shown in box number 1 here, which is based on program node graphs, where we can calculate from a node graph this complexity metric. Now, there is a precedence of this being used in multi-agent systems, looking at the connections between multiple agents in a multi-agent system. But we wanted to look at this from the perspective of individual plans within an agent. And so to do that, we drew node graphs, such as the one shown on the right side of box 3. And this one is actually for the collision avoidance behavior in the idiomatic agent. And using those node graphs, we were able to calculate the cyclomatic complexity for all of the plans. But there's limited examples out there of people doing this in AgentSpeak code. Now, that said, we were able to find that the lowest cyclomatic complexity actually seemed to be in our reactive and imperative versions, and the highest cyclomatic complexity was found in the idiomatic agent, which seemed to be because it had the most connections, those connections being to those prioritization functions that I mentioned. Now, that's software. Those are the software metrics, but as I said, we want to trade this off against the performance of the agent. And so we looked at this in terms of the agent's responsiveness. There's a couple of different perspectives that we looked at. First is in these charts on the right. Let's look at on the top, we have the perception period. So in the graph on the left, we have the perception period, and on the right, we have the reasoning time. Well, at least for the BDI agents, the reasoning time for the imperative version is just the time it took to process that if-then-else block. What we see is with the idiomatic and goal-directed agents, those reasoning cycles are generally very similar to each other and on par with the perception cycle or the perception period. We saw that the imperative agent or the imperative program was significantly faster than the BDI alternatives, and we saw that the reactive agent was a fair bit slower, and in fact it wasn't keeping up with the perception cycles. We'll talk about why that is on the next slide. Now, this was that difference in performance actually for the reactive agent meant that it couldn't keep up with perceptions, and it meant also that it couldn't keep up with driving the car, and in fact didn't even make it down the street to crash into the car down the road. It actually crashed into a fence to the right of the road on every single test. And so it's in these crash metrics for the collision avoidance scenario, it's not shown. But if we look on the right here, we have the idiomatic agent to my surprise, was actually outperforming the goal-directed agent. And we also found that the imperative version significantly outperformed both of the BDI alternatives, which sort of plays into the results we saw in the reasoning performance. Now, these results are reflected also in the crash rates. Now, when we drove the car at different decision points, so shown at the bottom is we have the range from the obstacle before the car needs to make the agent needs to make the decision to stop the car, and so for 5 meters, every one of the alternatives crashed on all 10 tests at that distance. But as we move out in increments of half a meter, we start seeing that the imperative version for its 10 tests at each of those distances stopped on almost every case. And the idiomatic agent, similar to those decision times, was outperforming the goal-directed agent. And so that led to another question of why was this happening? Why is the reactive agent slower and unstable? And why is the idiomatic agent outperforming the goal-directed agent? And so to look at this, we did profile tests. So we took those logs from the agent runs and we put them into a standalone JSON project and ran this with JProfiler and looked at the differences in the run times associated with the different methods. And it turns out that the difference in performance was tied to rule deliberation. Now, what's interesting about that is that, in fact, all of the different BDI agents had the identical sets of rules. The only difference was which rules were in scope for the reasoning cycle for rule deliberation in the different for the different agents. And at the collision avoidance case, the idiomatic agent only had 1 rule to process. The goal-directed agent had 4 rules to process, all the rules for driving, for controlling, for making decisions about driving down the road, as well as the collision avoidance rule. And the reactive agent had all 7 of the different rules available to the agent in scope for every reasoning cycle. And what we found was that led to quite a significant difference in performance when we looked at it with the profiler. And if we want to see this in terms of what crashes look like, well, here it is. So here on the left is our car crashing because it wasn't able to, it didn't have enough time to make the decision to stop. And if we look on the right here, here's an example of the car managing to hit the brakes in time and stop prior to colliding with its with that car parked down the street. Now, there's a number of limitations to this work. I've sort of hinted at some of them on the way. First off, from a validation perspective, we focused on just an individual use case, this collision avoidance scenario with the AirSim car. So this ties into some future work, which could be to do additional case studies, perhaps different types of agents, and also different types of agent methodologies. So look at different types of environments as well. And then also from the perspective of metrics, there seems to be a lack in consensus on the types of metrics to use for evaluating the software properties in AgentSpeak code, as well as a lack of formal definitions, at least that seems to go along with that, for things like coupling and cohesion, for example. And so I think something that would benefit the engineering multi-agent systems community, especially in BDI, is to look at the agent-oriented software engineering metrics and look at developing formal definitions for these types of metrics, and perhaps expand the metrics, at least the way that I use them, to other types of agents, and perhaps challenge the way that I've used those metrics, that we've used those metrics, to see if that holds out for other types of agent behaviors. To summarize things, we've assessed the performance implications of various design choices, and we've looked at this with simulated car stop trials, where we drove a car towards an obstacle on the street to see if it would stop in time. And we looked at this with 3 different alternative agent implementations, plus our imperative program in Python. And in doing this, to look at those alternatives, we compared those software implementations using the concepts of coupling, cohesion, and cyclomatic complexity, and we've applied those concepts to AgentSpeak code. And in doing that, we found that looser coupling and higher cohesion seems to be tied to an improved responsiveness of the agent. That's seemingly being tied to the rule deliberation and the processing that goes along with that. Of course, this was inversely related to cyclomatic complexity. With that, I'd like to thank you for your attention and look forward to the rest of the Engineering Multi-Agent Systems workshop. Thank you.